do a reinstall of this. I don't even have authority to do a reboot. It's such an old PC, I can't even find the frickin' power button. It's not on the front. I think it's one of those old school PCs that it's like, I think somewhere in the back. And I have a feeling it's Windows patches that are needing to be installed, but it's not even doing that. So, but at least Adobe Acrobat works. So we can do what we want, you know, what we need, but I just won't be able to use that functionality of the recording. So you guys are blessed, but your classmates may be screwed. So thank you for coming. I think when you know or anticipated being recorded, you can kind of like mentally check out and think, oh, I'll check Berger out on the weekend, you know. But so it's good that you guys showed up. Okay, we've got the second midterm on Monday, and to be crystal clear, this is kind of launching into the old former 432. It's basically two-terminal junctions, diodes, and diode applications. That's basically the theme: diodes, diode applications. And I did have this review. This was just sort of a legacy, but this is not the element of your testable material. This is all regurgitation of the previous midterm. I'll hit you on the first midterm when on the other flip side when we get to your final exam. The final exam will be holistic, so don't worry about that. But you know how we build on the vocabulary of everything. So it's PN junctions. And in fact, it's not solely PN junctions, because there's going to be metal semiconductor junctions and hetero junctions and things like that. But junctions and junction, applications, right? And this is all just sort of like a window, eye candy to kind of flush things out a little bit. We've gone over some of these, or at least I've kind of alluded to them in class. But these are not the basis, and I don't even know if you see all these because I think I have them turned off. That's not the element of testable material. So really, it's just these two PDFs. Now, this happens to be 129 slides. It's fairly dense and meaty, and this is the core of it. And then the next one, the diode applications, I get a little verbose and I talk about a bunch of stuff, kind of giving you the big picture. So although it's a 207 slides, it doesn't mean that this is weighted more heavily. This is kind of more just icing on the cake to see how these diodes, these junctions operate, right? So so don't think by the page count. The weight is towards the applications. The weight is here. And so you got to walk before you run if you haven't quite gathered how my class works and what I emphasize. So even the beginning of this is really off limits because this whole slide deck starts off with ways to process. And we covered this. This was embedded in the earlier midterm, and it's kind of just, this is just highlighting alloying, epitaxial growth, diffusion, ion implantation. We covered all that already. So you can basically go fast forward, LP, all the epitaxes, the alloying, the diffusions, the epitaxes, the diffusions, the ion implantations, right? You just hit forward, 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 forward. Even though gives you a little stuff on the advanced processing that my 5037 class was just doing. Really, this is where you start. This is and this first one, you can almost guarantee that there's going to be a question coming out of the how you launch, how you understand the so just fast forward to slide 22 and pick it up from there. So PN junctions, when wondering if I should lose this. He's trying to record me there at this oblique angle. I did want to use a little board work.
It's doing well. It might have a hard time seeing the actual screen. I might move over there.
Gotcha.
Yeah,
Okay.
and I just want to see it so to make sure that it's always videotaping. So
Okay. So the way the story goes, it's like this. We've got a P-type material and an N-type material. And so somewhere we're going to have P sub P and N sub P, right? And these are identified by what? This is Ni squared times P sub P times N sub P, right? And that's how we delineate it. So this is on a log scale. And so this might be 10 to the 18 per centimeter cubed. Who knows? Maybe this is 10 to the 10 to the 2 per centimeter cubed, perhaps. You know, they're sort of fictitious. And then we have N-type over here, and similarly. And so maybe I've got N sub N about 10 to the 17. And so then that would make my P sub N be about 10 to the 3. I'm kind of keeping it in the context of thinking about silicon, you know, where Ni is. So then Ni squared is equal to P sub N times N sub N. Right? So this is where you pick up the story. We had learned about this, each of these isolated semiconductor systems in the first midterm. Now we want to make a junction, right? Be an epitaxy, diffusion, whatever. We're putting these two together, and something magical happens. We have, what do you call that? Huh? Well, before you even get to the p-n junction, what is, I'm going from here to here, I'm going from here to here. I have
electric
There's the
field.
point at which the net carrier concentration goes to 0.
Electric field.
Magna, help me out. It's a concentration gradient, right? It's a concentration gradient, right? Because carriers move by either electric field or diffusion. Electric field is the drift, and diffusion is driven by the concentration gradient, right? So by just drawing this diagram, it should scream at you that I have a concentration gradient of 10 to the 17 down to 10 to the 2. 15 orders of magnitude with an abruptness, once I've married these together, of 1 atomic layer by this Kadonkin experiment, right? So I have 15 orders of magnitude driving this thing. So what happens? Oops. I have a crazy amount of electrons coming this way, a crazy amount of holes going this way, right? So holes, diffuse, electrons, diffuse. So now I've got this is N-type and P-type. And so holes are going this way, electrons are going this way, holes are going this way, electrons are going this way, right? Where are these electrons coming from? No.
The supply of electrons from the N-type.
And what supplied the electrons on the N-type? Who said doping? Surely, yes. And so say something more about doping in this particular case. So what's the dopant? Yeah, but what does that mean, an N-type dopant? Give me an example of an N-type dopant. Huh? No, the host, the semiconductor, is silicon, where Ni is about 10 to the 10 centimeter cubed. Yes, phosphorus. So what is representative of phosphorus versus silicon? An extra electron, right? Right? You got 4 covalent bonds, you got a 5th one, so this donates, right? Where did that donation come from? I mean, where did that electron come from? It came from the phosphorus atom. And what happened to the phosphorus atom when it donated, when that electron came across by diffusion? What's the state of that phosphorus atom in after this diffusion? Yeah, who said excited? Yes, it's excited. It's positive 1 plus 1, right? So as these guys leave, then that's leaving behind. And this is fixed ionized donors, right? And these leave behind fixed ionized acceptors. So the electrons come this way, the holes come this way. So after a little while, they've kind of done their thing. Right? So they're kind of out of play because they've already kind of been swept on over to the other side. And I'm left with these ionized donors and these ionized acceptors, right? And they create this dipole, right? There's a dipole. And so as this dipole opens up, we get a dipole of charge. And the density of this row is going to be tethered to the 10 to the 17, right? It's that. And this is going to be 10 to the 18. Right? And the dipole is equal, so however, I guess this is probably maybe a little longer, perhaps, and this is a little deeper. But the areas should be equivalent, right? And so you run Gauss's law on that, and you end up with E max. You integrate that, and you get your electric potential. And so it ends up being that you finally equilibrate to your so I've got N-type over here, P-type over here, I have a EFP, I have a EFN, EC, and ED, V. And I have manifested in this potential difference that is a manifestation of the triangular electric field, which is a manifestation of the rectangular doping profile that was revealed as the Red Sea parted. It's like Moses parting the Red Sea, I guess. And so then you end up with this potential difference. So this here would be your V naught. Therefore, this would be your V naught. So where does it start? It starts with the concentration gradient, which drives the diffusion, but concurrently it has a collateral effect. Everybody knows what collateral means, right? Consequence and the effect. Because of this, this happens. If this, then this, right? Just logic. So if this, then I lead to the ionized donors and acceptors, which creates the electric field. So the electric field grows, 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 right? It moves down. So why does this stop depleting? Why doesn't this just deplete all the way out to the very end? Why doesn't this like have a chain reaction? It's like Chernobyl. And it's just, why does it stop?
There's a limit of the amount of the atoms.
Huh?
There's a limit for the atoms.
No, no, because it's going to be, it's going to be like 500 microns.
I remember you talking about something holding back the flood, similar to the Kurds. The political references.
Yeah. You can almost guarantee this is going to be on the exam. Okay? And what caused the drift?
The black hole, the fixed power lines.
So what's the drift doing?
So it's holding the diffusion direction back
How is it doing that?
by the electric field generated.
The electric field. Yes. Sorry, I was playing coy there. But yes, you were right on track, right? So the electric field, that's why the bands bend. That's why I drew this. The dipole creates the electric field. The electric field indicates there's an opportunity for the drift that Shirley talked about, right? Which bends the bands. So the integration of the electric field leads to a potential energy difference that is parabolic in nature, which manifests, maybe it's more brilliantly drawn over here, as this p-n junction, where I get this concave down here until I get to the metallurgical junction, and then it changes concavity. But that's a finer point. But the electric field leads to the V naught. So the V naught is trying. So as these try to diffuse over, the electric field is pushing it back, right? So any electron up here wants to roll downhill, right? But I have more electrons here because this is the majority, right? And I have more holes because this is the majority, right? So they want to go this way by diffusion, but drift wants to put it back. So I need from my Chinese students to tell me, what is that?
Yeah.
Yin yang, right. Bingo.
So all the electrons creating the. Okay, so the electron can't come down because of the electric field created by all those electrons.
Yeah, the electric field is trying to push it downhill, right? They just fall down.
So if the electric field is trying to push down, what's keeping it up?
Concentration gradient. Because you
Gotcha.
built the signs.
I have an electric field. It's all this ballet. It's all working together. And if you can draw a band diagram, you can understand the dynamics. Because I've tried to teach you about the carriers, where they are, where they're not. right? So you have a little abbreviated one down here, right? So this is my N sub N's, these are my P sub N's, right? These are my P sub P's, and up here I have a small little N sub P. Right? Zane, you with me? Good. Yes.
So you're saying because of the diffusion of the electrons from the N-type, can we build the drift of, or you're saying the drift of the electrons from P side can repel the diffusion of the electrons from the N side?
Yes.
So
Yes.
what about the pose?
So that it opposes. Yes. So the way I usually phrase it is that because of the concentration gradient, it leads to the diffusion, but the diffusion leaves behind the ionized centers. And the ionized centers create the electric field dipole. The electric field dipole through Gauss's law leads to the potential energy difference, which leads to this yin-yang, right? I got the drift is the diffusion wants to go this way, but the barrier holds it back. The drift wants to go this way, but I got a limited number. So this is large, but impeded by the barrier. This is small, but there's no direct impedance. It's just the availability of the carriers. So the drift and the diffusion. So it's zero bias. I, V, zero bias, I get no net current, right? No net current. I have an absolute current. I actually have a finite amount of diffusion, finite amount of drift, finite amount of diffusion, finite amount of drift. Right? All four current components are they're non-zero, but they all balance each other, and I get 0, 0. I get the origin. So as the barrier lowers, so I apply a forward bias, the V naught is lowered, and this starts to take off, right? So this goes up exponentially. And why does it go exponentially? Because this is walking up exponentially right there. That's what you see here is revealing your Fermi-Dirac statistics. Direct one-to-one correlation. So this comes up, you're peeling away these carriers, which are going up by the Fermi-Dirac statistics, which is exponential. Same.
And so what really limits the size of the depletion region is just that you only have so much interface. And the fact that there's only finite PN interface area really limits the effect of it as you go outward, right? Because then the diffusion can't be as much, even though the drift could. Is that the right way to understand it?
No, I would say, so you're right, I didn't come back to that question yet. So the question could be on the exam of why does it stop, or maybe it needs to be for a full point answer. Why does the depletion stop? Why does it hit this? And it's at a certain point, the Fermi levels align, which slows down the driving force. The barrier is of a certain size, and therefore, at that particular point, the drift and diffusion are balancing each other out. Until it got to the V naught, the diffusion was greater than the drift, right? It was continuing to trickle over the top. But when it finally got to V naught, that's the magic where drift and diffusion balance, yin and yang are in harmony, right? It's feng shui, right? And so therefore therefore it stops depleting. So I'm at the V naught. Okay. So what happens when I go reverse bias?
V naught goes up.
Less current flowing because it's a larger V naught.
Yeah. And what is the source of this current? Tell me. You're right. Tell me more. That's not full. That's not a full point answer. Let me phrase it that way. Okay. No, you're trying to get on my good side. No. Yes, same.
Well, the thermal generated carriers in the depletion region, they got a good chance of kind of falling down the slope.
Right. Any generation here, carriers will create electrons, holes, which will be collected and, whoops, wrong way, which will be collected and manifest as a reverse saturation. So the proper answer is in or near. So you have to consider LP, LN, right? It's the W and the diffusion length on either side of the depletion region. Remember, we saw this when we got to photodiodes. So it's the in or near. When we got to photodiodes, we tried to shut this off. We didn't want this. This was a slow component.
And those are electrons that jump up in the depletion region there.
Yeah, that's just my KT scrambling everything, right? Don't forget that I've got a KT running around at 26 milli electron volts, scrambling everything. So it's there's generation recombination happening everywhere. It's happening here, it's happening here, it's happening here, right? And so carriers are just like Mexican jumping beans. They're just going up and down. Okay. So I'm going to go back to the slides. Timed out here. So as the carriers diffuse across the junction, it produces, let me magnify that. All right, so I started off with, think of the N and P regions being separated using the carrier statistics here. We see a small number of minority carriers on each side of the junction. We see a large potential for carriers to diffuse. That's the meaning of concentration here. So as the carriers diffuse across the junction, it produces that charge imbalance by the ionized centers. These ionized centers create an electric field. The electric field opposes the diffusion, and eventually the diffusion electric field reaches equilibrium, and the resulting charge region is called the depletion region. That's about as brief as you can get. But you end up with that. And so here you can see from the modular series. Okay. So you're scaring me, because this should have been fundamentals. Okay, so then we have it depletes, create the space charge region or depletion region, creates an electric field. We have positive charge, negative charge, and is this charge moving around? Where's this charge come from again, Del? Matthew. It's the ionized donors and acceptors, right? So therefore, it's free or fixed? Fixed. Beautiful. Good. So, yeah, this is what I was trying to draw before. I guess maybe I should have drawn it up, but anyway, you get the idea. I don't know, maybe I was inverted. Yeah, no, okay, so my bottom one was the wrong polarity. And then just to remind you from the first midterm, we have the intrinsic carry concentration going on. So as you change temperature or change band gap, right, the intrinsic carry concentration is changing around. So that leads to, when is this in harmony and what is the temperature immunity. But here's showing the drift diffusion, right? Basically, it's what I drew over here. And so then, as you apply a bias, lead to the carriers, electrons go downhill, holes float up. And so as we apply a bias, we get the generation current, diffusion current, and so here's the Gauss's law and depletion and so forth. So we have this this row and the electric field. This is a fairly one-sided junction. So if you got 10 to the 18 across from 5e15, it's going to be more of a right triangle almost like situation where the depletion region extends minimally into the highly doped material. So then, so this is the forward bias. Right. So as the barrier lowers, the diffusion takes off, and that's why in the forward bias we refer to it as this is the diffusion, and this is the generation down here. So this is the diffusion because the diffusion is enhanced. The drift, did the drift get any faster or slower under forward bias? No.
Probably gets even slightly worse, like undoing the effect of the forward bias, but it's still starting to end up, right? So you end up with more carriers.
Technically, I would say that it's technically it's still drifting because you still have generation in and near the depletion region. It still goes on, but it's just almost zero. It's a negligible portion. So people usually don't worry about this. It's this the mother load is coming the other way. So yeah.
So normally, at zero bias, the drift is like undoing the diffusion.
Yeah.
Because they've all got equal zero bias. But so it's the diffusion that does most of it when you bring it into forward bias. What's going forward, right? Isn't the drift still undoing it? Isn't it more like diffusion minus drift? Because as you diffuse,
Yeah, it's going the other way.
Yeah. Okay.
Yeah.
I see.
In reverse bias, is drift increasing or decreasing? Or is it staying constant?
You tell me.
I mean, I don't think it's being limited. It's staying constant because of the...
It's staying constant in our ideal case. But when we get to non-ideality, it's changing.
Well, as you apply reverse bias, might the size of the depletion region change?
Yeah.
I think it's wider, right?
Correct. So, so in reverse bias, right? It's the diffusion is valved off because the barrier is now so large, and there's current continuity. Holes going one way finally get recombined, and they turn into electrons coming the other way. So there's a current continuity. So holes in plus electrons out equal the total current. So there's current continuity. It's just that you have to kind of wrap your head around that it's holes going in one direction and electrons going the other direction. And so don't forget that this leads to, under forward bias, it leads to an accumulation of excess electrons on the p side due to the excess diffusion, right? So they pile in, and they're swimming around over here. And these are swimming around over here. There's an excess of them. Right? So that's what this is. And so then if you get the derivation of the ideal diode equation, you can think of the charge control model, where it's basically predicated on that the Q, that excess, is being replaced every tau n seconds. Where over here it's every tau p seconds. And so then you can derive that, put it all together, and you find out what the electron component is, plus the electron current component and the whole current component. You add it all together, you get the total current component. So you can derive basically the diode equation from first principles. There. And you end up with these parameters here related to the diffusion coefficients, the carrier concentration, the characteristic diffusion lengths in the materials. These are all parameters that can be calculated or determined once you know the semiconductor, or the temperature, or the band gap, the doping. You can figure all of that out. Yes?
Do we need to know this thing for the exam?
No. Again, it's going to be qualitative on the exam. And, so then you start to get into the bias dependency, the switching, where you're going from a turn on to a turn off, right? So this is the turn on where you get the excess, right? And then when you turn it off, when you go into reverse bias, the diffusion is very much suppressed. So you're not having yin and yang, so therefore you're not at the equilibrium values. Really, you might want to call this NP naught and PN naught. And so therefore it's going up and down. It's the dog tail wagging. So then after, and we'll get back to that a little bit later, but the reverse breakdown mechanisms, they're twofold, right? One is the Zener. So at some point, we get a reverse breakdown, boom, and one is going to be due to Zener tunneling, occurs at a few volts, and if it doesn't happen right away, then it's going to be an avalanche. And so the Zener tunneling is when this is fairly highly doped, so the Fermi level is really near the valence band and the conduction band, and as you bias it, the available carriers, remember this is filled with electrons. The holes are like little air bubbles that percolate up to the top of the valence band, right? But the rest of the valence band has got your 1s electrons, 2s electrons, 2p electrons, right? This is just riddled with electrons, right? 4 times the Avogadro's number, essentially, of the electrons are filling down here. This is an ocean of electrons. And so you're always able to peel off the top of that onion. It's like an onion where you're just peeling off layer after layer. You're able to peel off the top of the onion and throw that over here. This has also got 4n density of states up in the conduction band, but this is usually filled, this is usually empty. Remember, that was the band gap when we partitioned it? The 8 states went into 4 down here and 4 up here with a band gap in between. So I have plenty of electrons here, plenty of empty states here. And as I bias this, I'm just peeling off layers of an onion. And so this continues to go more and more. I take off one layer, and I got another layer behind it. So this just continues to plow downward. Right. And so that's what I was trying to draw here. It's kind of reminding you that the density of states is kind of a primitive cartoon, but it's kind of trying to remind you there's electrons down here below the holes. And there's a puddle of electrons at the top, but generally empty space above it. So the avalanche is when you bias it, put this really into hard for reverse bias, then a carrier can eventually, it's like grandma falling down the stairs, right? Eventually it gets to be too steep and boom, boom, boom. And maybe that's a bad analogy. Sorry. and so you're hitting a kinetic energy where this thing is accelerating so much that when it hits and scatters off the lattice, it's delivering enough kinetic energy that if it's equivalent to the band gap, it can create the creation of another electron-hole pair. So one electron in creates two electrons out and one hole out. So one carrier creates three carriers. One carrier creates three carriers, right? And so it cascades like that. So this is the avalanche. So avalanche, it's like Chernobyl. So, so here it is showing it statistically, sort of at the bias, as you ratchet up the bias, this is kind of, it's just starting to hit the threshold where you're starting to get this, but it really has that cascading runaway effect like a nuclear meltdown when you start to get the bias up even more. And this carrier creates an electron-hole pair, and this one goes and it creates another electron-hole pair, and this one, so now one electron in is creating 4 electrons out and 2 holes out, right? So one carrier led to a multiplication of five-fold there. So the tunneling happens at very high doping. Very high doping, because it either happens right away or it doesn't happen at all, and then it's going to be the breakdown due to the avalanche. So it's one or the other. Zener happens right away or it doesn't happen at all. You're not going to have both. Devices really don't have both. Special case was I was getting into that punch through where the depletion region extends, and that led to that special case also later on where we had a short base diode or a rapid switching.
What's the punch through?
We had the case where
Oh, I think you were telling me that. Go on.
so this is the excess, right, switching, and so I got to add and subtract this, dovetail. But what if I make it a short base diode where this is the surface? Then that means that it's not this, it's got to go to this. This becomes a boundary condition. It's got to go to 0 because this is the surface, this is where the metal electrode is. So it limits, it's called the short base diode. It's kind of a special case. So you can speed up the switching.
Oh, so it sort of limits the area under the curve, and that has to do with the time.
Bingo.
Okay.
Yes. Yeah.
And where's the punch through?
Oh, the punch through was where it was kind of the setup for that. Is that the depletion region can extend also to the point that the depletion region actually hits the ohmic contact here. It punches through all the undepleted.
Uh-huh.
So this T goes to 0 at a certain point. A very special case. I can guarantee you it's not on the exam. Okay. So switching dynamics, the minority carriers, we have the junction capacitance, the minority storage capacitance. So understand those. What's the junction capacitance from? The dipole. Right? And what's the minority carrier storage charge from? it's the excess charge that is the PNPs and the NPs and the PNs that were accumulated under forward bias, reverse bias, forward bias, reverse bias, right? So the add and subtracting that. So, switching dynamics, you're basically just looking for a capacitor. And in this case, in the junction capacitance, well, to give it away, junction capacitance is talking about the junction. So, therefore, it's the junction of the dipole of the junction. And the minority carrier storage is talking about minority carriers. And where's the minority carriers? Well, they're outside the junction. So this is the one that's inside the GUI center. And these are the ones that are outside the GUI center. This is where it's undepleted. The depletion region is in here. This is W. That's W. So this is happening out here. Right? So there's a dipole in the middle and a dipole on the outside. So they don't make screens like they used to. So here's the dipole of the depletion region in the middle. Right? You're just adding and subtracting little slabs depending upon whether you're doing a little delta plus voltage or a little delta minus. Whether it's just a small little perturbation. Right? You put a tickle on that. And so then that manifests as the capacitance is varying as you go through the bias. And so it becomes less. Why does it become less important under reverse bias? The dipole?
Why does it become less capacitance?
Yeah, the capacitance is going down. You would think the depletion region is growing, right? So there should be more capacity, more depletion, right? More depletion, more ionized centers. Shouldn't this capacitance go up?
No, it's because only the non-fixed carriers can participate, right?
It's the slab. It's really like a transient, right? It's a transient. It's not really a DC parameter. It's kind of a AC. It's the delta. If I do a small, if I'm ratcheting the voltage by increments of 0.1 volts, plus 0.1 volt or minus 0.1 volts, I'm adding or subtracting little slabs. And so it's the delta rho. If you go back to the capacitance, it's not the absolute charge, it's the change in charge leads to the capacitance, right? It's dq dt. dq dt. Go back to your basics, right? So the change in the Q as a function of time is the slab, not the absolute amount. And so then you're right, was it Shirley or Zane said, that the depletion region's growing, and so therefore the distance is, so therefore it's dropping down. Right?
You mean a DQ dV? Or
DQ dV. And so you can use that for tuners and all that stuff.
I think there's got a question.
Oh, sorry.
Is it also related to that C is equal to permittivity times area over D? So as depletion region widens, D increases, that's
Yes.
the capacitance
Yes.
goes down?
Yes. C epsilon A over D, and you can normalize by area, so it's really the epsilon over D, and D is getting larger. Yeah, we use this equation more when we get to the FETs, but yes. Okay. Sorry, Megan. So the charge storage capacitance is related to, yes, dq dV. And so here it is. So then you go in and you plug in from the analysis of the waveforms. You can throw into there the diffusion lengths and all those parameters, or the recombination lifetimes, whatever. whether you want to be, but it's really predicated on that the charge is, the current is the charge being replaced every tau p seconds. So this is just rewritten in a different form, but it's the charge control model. So switching response. Why does a large reverse current flow momentarily? Do you remember that one? Why does, when I'm switching this, when I'm going from forward towards reverse, does it flow a large reverse current and then it decays? Right? Why doesn't it just go? Wouldn't you think that it would just exponentially decay from here down to here? Why doesn't it connect up as a concave up waveform? Why does it go full on negative and then exponentially decay concave down?
This is because the voltage would be held constant until it reaches like the origin point, and then all of a sudden, like a large amount of current will start flowing. Is it?
You get full points. Yes. Because it's until this is depleted, you are holding the bias across this junction is the diode thinks it's still in forward bias because it's on the top side. Because all this is forward bias, right? All this is forward bias. So it doesn't matter if it's a lot, medium, or small. Until it hits the zero, it remains as if it's forward bias, and the forward bias voltage is very, very minimal. And so one of these shows that, I think this one shows it a little better. As if you're going forward, reverse, looks like your old linear circuit theory circuits, right? So you got this diode, but you're switching from a reverse power supply to a forward power supply, and you got that one of those T=0 switches. Remember those? Probably have nightmares about that, right? And so this goes full on negative because Kirchhoff's voltage law is when it's under forward. This had, if this is a silicon diode, the cut-in voltage is 0.7 volts. So I have 0.7 volts, and maybe this is a 5-volt power supply. So I'm dropping 4.3 volts across this resistor. I'm flowing a lot of current, and most of the voltage is dropping across this resistor. And I flip this. This stays at 0.7 volts until the charge is lost. And now I've got maybe negative 10. So I've got negative 10 plus 0.7. So I've got a large negative current until this finally starts to take on the negative flavor. And then this starts to reduce the amount of current. So if I take this magnification.
And that's basically from pulling the minority carriers kind of on the wrong side back to where they.
I would not phrase it that way. You're not pulling them back. They are. It's the answer you all usually give me.
Generation.
Yes. It's the recombination.
Oh, so you just
Generation.
have to wait for the time constant to go by.
You wait. You sit there with a stopwatch. You're waiting for Minute Bolt to race past you. Not Minute Bolt. Usain Bolt. So yeah. So T=0. It wags down, wags, hits the 0 point, and then it starts to take on a negative flavor across the diode, and then eventually. So then your waveform, the current waveform actually looks like that. So your digital waveform in is being corrupted in the current domain space. Okay, deviations from ideality. Hopefully we can do this quickly. Why is this one? Kind of talked about that already. Why is this not staying steady? This is getting larger. Zane loves this one. Zane, you want to do this one?
Oh, it's the depletion region is increasing in size of the reverse bias.
Yes. So it's the carriers that are being generated in or near the depletion region, and because this is a strong reverse bias, the depletion region is much larger, so the volume that is collecting that generation is larger, so it linearly increases with voltage. We already talked about the breakdown. We have the recombination, because we're still not at the sweet spot, right? As this goes into forward bias, we're still not near the sweet spot of where the carriers are. We've got, this is kind of a dull space. There's not a lot going on here, right? This is the sweet spot where most of the carriers are. So the initial part, till we get to that like cut-in voltage, not much happens. So we're still in this generation recombination domain space, and that has an n equals 2 ideality factor. Then everything gets nice and happy, right? We're following our ideal diode, n equals 1. And then we get really forward biased. And why does it go back to n equals 2? Recombine, yes. So this is when it's the high level injection. So we have all these carriers coming, and so now we have them slamming into each other. They're becoming so plentiful that the electrons going this way are slamming into the holes coming this way, and there's recombination happening of the free carriers and that are circumnavigating. So there's lots of collisions, right? It's getting to be very crowded. And so there's lots of collisions, and then as it's passing lots of current, it gets I squared R joule heating. It starts to heat up, and as things heat up, the resistance goes up. So it's kind of this nonlinear cascading runaway effect, and eventually it's just going to melt. I mean, my students will usually push the diodes that they make to the limit and see when we usually have a microscope and a digital camera, and you can see as you're biasing it, and you'll actually see it burn. You'll see a little puff of black smoke in a device, and then you kind of know what your limit is. And so we learn something from that, from the failure. So obviously you can discern from things like the cut-in voltage can kind of give you some indication of the band gaps, right? Because there's some scaling. Obviously there's some fudging that left or right based on the doping level, but if all things being equal of doping, this would be indexed by their band gaps. And so we get the recombination. I think we kind of talked about that. So special case, you can make junctions linearly graded, right? So therefore you can, but let's think about the metal semiconductor. We kind of talked about this more recently as we got into MOS, right? We have the work function of the semiconductor, work function of the metal, which leads to when they line up. Remember how this works? Band diagrams. This kind of locks together like Legos. And so this clicks right here, this clicks right here, and that becomes the where it's glued together, and then it has to align the Fermi levels. So in this particular case, we have the Fermi level of the semiconductor is higher than the Fermi level of the metal. So therefore, this N-type material is electron rich, and so for these to align, the N-type material has to become less electron rich. And how does a N-type material become less electron rich? Yeah, that's not the word I would use. Donate, diffusion.
They're ionized maybe
word I would use is deplete. Creates a depletion region, right? Depletes them. So it creates the dipole. So it depletes, pushes the electrons away, creating the electric field, the dipole, the electric field, the bands bend. Bands bending means there's an electric field, means there's charge. Right.
And so you just do this with an N-type semiconductor because it wouldn't form the barrier if you did it with a P-type, right?
This is a P-type material, which means that it's really hole dominated. And so you fashion it in this way where the Fermi level is very low for the semiconductor with respect to the metal, and it forms a depletion region. And this is P-type material, which means there's a predominance of holes here, and the holes have a barrier to come. So this rectifies the holes, and the other rectifies the electrons, but they both rectify, they both make a rectifying diode. This is how we make rectifiers for RF Wi-Fi energy harvesting for our printed Internet of Things objects, for instance. We just make a simple Schottky, and with an evaporated Schottky that has this behavior, and then we can harvest energy and trickle charge and run our Internet of Things objects. My master's student just graduated on some of that. So it behaves as your normal diode. It's kind of like our PN junction. Forward bias, the barrier lowers, carriers splatter over the top. Reverse bias, the barrier increases, the diffusion is prevented, but the reverse leakage current by generation near this junction still continues, and so you still get the leakage. So it behaves very similar to a normal PN junction. It's called a Schottky diode versus a PN junction diode. And so if you want to make a low resistance Ohm contact, which my 5037 classes may be, I'm a little skeptical about I'm a little dubious about the quality of their Ohm contacts, but this is what they were trying to do. They were trying to make an N-type contact to their semiconductor, and so you evaporate a metal, and if everything goes well, it leads to an Ohm contact. So there's very minimal barrier for electrons to flow between the metal and the semiconductor, and this P-type material, there's very few barriers for the holes to go back and forth. And practical diodes, well, we normally actually get Fermi level pinning due to the interface states of the surface. And so that can plague and lead to a Schottky barrier height, irregardless of what metal you use, regardless of the choice of metal. So you use aluminum, gold, silver, tantalum, titanium. But in this particular one, of indium arsenide, it's really easy to make an Ohm contact. Heterojunctions is where the fun is, because now you've started to see the LEDs, the laser diodes, things like that. And so then we're just playing with the band gaps and making these heterojunctions. So this leads to a beautiful bipolar junction transistor, but I haven't talked to you about that yet. But here's the discontinuity, and you end up with the ability. And so then we talked about this as a HEMT, because we just talked about field effect transistors, a MOSFET, HEMT. And then we get into diode applications. And you can see rectifiers. If you want a good rectification, you want to minimize, you want to make it full on or full off, right? So you want to, for the off, you want to minimize the reverse saturation current. So maybe a wide band gap material, which lowers the Ni, which lowers the I naught. So therefore, it brings this up, makes this more like a flat line. reduce the power losses, so we don't want this to bend over. So we make it increase the area. So the I squared R joule heating is minimized. We highly dope the contact because we just showed the element contact, so we want to increase that. We want a high breakdown voltage, so we don't want it to stay flat line for as long as possible. So then maybe we use wide bandgap material on one side. So the high critical field is dominant on one side, or use a one-sided junction. So the lightly doped side governs the breakdown. Switching diodes, right? That's where it's going back and forth. So we can add recombination centers, so we can enhance the recombination lifetime. So it can bring it down very quickly. The narrow base diode that we were talking about before, kind of a special case, shorter than the minority carrier diffusion length, so the carriers don't have to diffuse very far to get to the contact. Breakdown voltage, tunnel diodes. So as you have, actually probably, yeah, this is kind of, so you can see the keyhole effect. So we got as doped so high, actually let's start here. It's doped so highly that I have a lot of holes here and a lot of electrons here. The Fermi level is in the conduction band. The Fermi level is in the valence band, so we never saw that before. And so as this goes, the two keyholes align. This is available carriers. This is empty states. So I have available carriers opposite empty states and a small distance in between. So I get tunneling, quantum mechanical tunneling. Tunneling starts to detune, goes through a valley, and then eventually the forward bias diffusion current kicks in. And in reverse bias, we get Zener. But the Zener happens immediately. So reverse. It's like a Zener dot, but yes.
The thermal diffusion current, is that the same as hot carrier injection?
No, this is just your normal. This is your normal diode. I drew this once a long time ago. Essentially, you have a wire there. The tunneling does the hump, and your diode does the normal diode. And so what you're seeing here is these two current components, the aggregate. And that's what you get. So over here is the normal diffusion, and over here is the tunneling. The camel's hump is the tunneling.
I see. Wait, so maybe I'm asking you to go back a little. What's the hot carrier injection? Like when, that detonation.
Yeah, it doesn't apply to that.
Yeah, I guess not.
I mean, it's just high-level injection is just that it's so forward biased. The carriers, it's almost going to flat band, and so the electrons coming. There's so many electrons coming, and there's so many holes that they're hitting each other as they're coming across.
Oh, and it's like
Because they're separated in energy space, but they're not separated in physical space. Right? They're going right past each other. Physical space, they're going right past each other. In energy space, they're separated. Right? It's a parallel universe, just like the Republicans.
Yeet.
You don't need to know RTDs because it's not formally in Streetman. So all that's just eye candy. Even that is okay. Solar cells. What do we want to do with the solar cell? Who's taking my 5237 class next semester? I thought there was some. I thought you were a role book, no?
Yeah, but it doesn't fit well into my schedule.
Fair one. No one else wants to take my 5237 class? Okay. Okay. Because they're in jeopardy of canceling one section. That's why I put some flyers out. Can you tell your friends who might be interested, who maybe didn't likes solid state a little bit, but maybe they had another professor for 3030 and they kind of want to get a taste, a new taste of it. So you get to make solar cells from scratch. And again, this is kind of eye candy and kind of explains everything, but essentially it's light comes in and a photon flux comes in and it's being absorbed in the semiconductor. So the intensity of the light is being diminished as a function of depth into the semiconductor material. So there's an alpha, an absorption coefficient. So as a function of depth. So two characteristic, one characteristic length that's down to it's diminished by 67%, and two, and so forth. So you only need to go 2, 3 characteristic diffusion lengths before you reach diminishing returns. And what is the root basis of the reverse saturation current of a diode? The reverse saturation current of a diode, this generation, is due to generation that is
in the depletion region or near.
In or near the depletion region. So what happens when I shine light on it? Don't you think my generation rate has come up, right? So then the whole curve gets shifted down, down, down. The more intensity, it shifts down, down, down. So you're just pulling the IV down, and so then it pulls down, and you end up with an open circuit voltage and a short circuit current in the fourth quadrant, I guess, but it doesn't matter. I'm pointing to the fourth quadrant, and so that acts as a solar cell. So this is one of the ones we make in the second half of next semester as a silicon solar cell with the screen printed electrodes like that. And you'll do a diffusion to make a PN junction. And yeah, so it's pretty much like that. And you look at the maximum power. And we do something where we kind of etch, and this is not exactly this. This is kind of a perfect grid, but we do something to etch to make it very rough, to cause it to improve its efficiency. We don't do this triple junction solar cell. We do this P3HT PCBM. This is the first one. You kind of cut your teeth, and kind of the first one to practice with. It's a plastic solar cell, so you make have these powders, and you make a solution, and then you spin coat it. So it's a functionalized C60 buckyball and so forth. But basically, the root basis is you're absorbing light near its band gap, and from that you're converting the sun's photon energy. So this is something I did a while ago. With this plasmonics. You've heard about plasmonics, so this is a plasmonically enhanced solar cell. I just saw some press release. Someone was talking about that Google paid money for this solar cooker. Did you see this on the news? They were talking about Google paid, and they made this. They had these mirrors that were using AI, and they were trying to heat up this tower by shining light, and they could get it up to 1,000 degrees. And it was on Gizmodo. Is it Gizmodo? You probably guys know that, right? And I tried to make a comment, but it didn't let me. And I was trying to tell them, BS. This is not the first in the world. I physically climbed up this damn thing in Uzbekistan, the former Soviet Union, and this whole mountain is wallpapered with mirrors. And this thing's 5 stories tall. It makes the thing Google did look like a little little boy with a magnifying glass trying to go after an ant, and this is way bigger. And I'm told that France has one too, and they can get up to over 2,000 degrees. I actually went up into the target chamber, and we saw the ores that they had melted. I actually held them in my hand. I might have even taken a sample.
You get a tan up there?
No, it was a cloudy, sunny day. Cloudy day, and so what do you think is better, the wintertime or the summertime?
Summertime.
Wrong.
My friend has very fair skin and he gets sunburns in the winter because the snow reflects onto him.
No, that's not the reason here, because that's an indirect. This is all direct light because it's got a ricochet. So no. In the summertime, you have a lot of humidity, and so that attenuates the sunlight. So in the wintertime, they get higher peak temperatures, but it's a shorter duration because the sun's up for a shorter amount of time. But you know, you look in the wintertime as we're getting colder and colder. On a really cold night, you look up and the stars look so crystal clear, right? And there's that haze in the summertime. So that directly correlates to a higher operating temperature in the dead of winter. Here's my Uzbek friend. He was the director of the lab.
Do you know if they need direct sunlight, or can it be through like,
No, it's direct sunlight.
or like if there's a cloud or overcast, do they still?
It'll attenuate, yeah. So undersea cables, we're not so much talking about this is a semiconductor class, so I'm not talking so much about the optical fibers. I'm talking about how to make a high-speed photodiode for optical communications. And for that, I want to have the PN junction. I want to collect, remember the light is attenuating e to the minus alpha x, right? So I need to make the semiconductor 1 to 2 microns thick. So that's why I do a PIN, right? A PIN photodiode. I used to build these all the time. Leads to a lot longer collection length, so I can collect a lot of the light. And because this the carriers are coming from in or near, by having this be highly doped, N plus and P plus, there really is no generation recombination here. It's kind of suppressed. The electric field is housed only here, and so that's where the generation is happening. So I've kind of slowed down, because remember, this near leads to a slow component of the collection because it's got a diffuse here, and then the drift is fast, right? So I don't want that slow diffusion. I don't want this slow diffusion. And so here I'm suppressing that by the PIN, P plus I, N plus layer. And why do we have the cutoff? What's the cutoff here at the long wavelengths? Band gap. Yep. Long wavelength means shorter energy, means that the energy is now no longer above the threshold of the band gap. And this is, the energy is getting higher and higher, so what's happening to the photodiode? The collection is getting tighter and tighter towards the top. So it's coming in and it's being absorbed closer to the alpha is getting very high, so the collection is happening near the surface. So now the surface recombination and all that dangling bonds are starting to suppress, so the carriers might not even get across the PIN junction. And we talked about this. The shoulders are due to the indirect band gaps, the participation of the phonons. And I won't bother with the CMAPD. That's a little more advanced device. Metal semiconductor, right? Reduces the capacitances for higher speeds. It's easy to fabricate. It's a majority carrier device. So we don't have the minority carrier storage, so it's much, much faster. That. Why is the sunset red? Right, because at sunset, it's going obliquely through more of the Earth's atmosphere, so therefore the shorter wavelengths, the blues, indigos, violets, all are scattered off into space, and the reds are the longer. You know, it's like the difference between a Mini Cooper and a Hummer, right? So the red wavelengths continue to come down. So you guys are probably happy. Blue's scattered. There's no more blue, and the red is persistent, right? Okay. So you've seen the poster outside my office in Caldwell with the millimeter wave sensing. The basis is the same. So instead of a Mini Cooper for the blue and a Hummer for the red, you now have millimeter is a 18-wheeler Mack truck. And that can plow through a whole lot of stuff, including a light jacket. And so that's how you seal a concealed weapon below a jacket, or a pilot can see through fog when they're landing their airplane. So it's like the analogy would be an 18-wheeler compared to the other modes of transportation. So that leads to the, then you get the fiber optics, so you can have dispersion, dispersionless fiber. You can easily make dispersion correcting fiber, but this is the Rayleigh scattering, the Rayleigh scattering that's attenuating, and then the absorption of the vibrational modes of the molecules themselves, atoms themselves. This was, I'm not really going to test you on this, but I thought you should understand where technology comes from, what are the innovations, and so forth, especially if you're a big gamer or YouTuber and big lots of TikTok or something like that, and you're a big consumer of the bandwidth, right? You should understand what engineers did to make your world happen. So we want light emission, the fundamentals, we just dial in the band gap. Right, so what material do we want? Do I want infrared? Do I want red? Do I want green? Do I want blue? Right? So we just designed our scarlet red LED for our class, and we're going to be doing, I forget the aluminum percentage we decided. So we'll have to see if we come close. So light emitting diodes, you know, there's a spontaneous emission, goes in all 2-pi radians. I'm not going to go over, I'm not going to test you as much on all these little fine different permutations. I kind of want you to know where this all comes from. This, by the way, if you're interested, these are this is, I should be probably teaching next year my 5833 class, where I go through organic semiconductor materials and the devices you derive from them. And the OLED here, so any of you have a mobile phone with an OLED display, my 5833 class will explain exactly how this happens. It's a whole new class of semiconductors, and it's predicated on these guys who won the Nobel Prize in Chemistry. And I'll explain all that. So really, the thing is, you know, you start to see how you can make PN junction, or you can make a double heterojunction. I think our LED for our 5037 class is going to be more simple like this. Just going to be a big sloppy double het like this. So it's not really going to have quantum confinement. Yes, Megan.
All the slides that you have like skipped through, do we have to know about them?
Yeah, that's what I'm saying. No. I want you
The
to.
ones you like stop and explain, those are the ones.
Precisely.
Right?
Yes.
Okay.
Yes.
Yes. The duration that I spend on it shows the importance that I put to it for your testable material. Yes, there's a direct one-to-one correlation. So yeah, so you can see, you can dial in the different band gaps. We saw this before on cut-in voltage. So you can dial in the different band gaps. So yeah. So then you can see that double heterostructure will have this slot. There's no quantum confinement in this big sloppy quantum well here, because it's really a double head, and so therefore the light emission is going to be smeared. Remember the word smeared? We defined that the other day in the lecture. So then, yeah, this is what we do in the solar cell. By the way, we turn it into this by some etching to scatter it. And lasers are just the application of a Fabry-Perot etalon. So we end up with these modes. So you have the spontaneous emission with the Fabry-Perot, so you end up with the multi-mode. And if you want to go to a distributed feedback laser, then through the the addition of a grating, you're going to be selectively, destructively interfering some of those modes, and hopefully reinforcing only one of those modes. So then it will be a single frequency laser suitable for your WDM wavelength division multiplexing application for long haul optical fiber. You don't have to do this if you're doing a simple laser pointer, right, or something like that. So that's pretty much it. Questions? I got 9:45, so we've been here for a little hour, 45 minutes, roughly. No, hour. We started a little late.
126 minutes of
126.
27 now of recorded material.
We're gonna call it a day. Go home and watch the news and find out if the Democrats or Republicans won.
Which side are you on?
I'm not gonna say here. You're recording. Yes, tell.
We go over like what it means for like the ohmic contacts again.
So just to be very clear, it's like a 2x2 matrix. So I have PN junctions. So Schottky can be P and N, and I can have ohmic contacts P and N. So it's kind of like a 2x2 matrix. So is it P and the metal work function is above the semiconductor, or is it P and the metal work function is below the semiconductor, right? And so one's going to be one or the other, and then you do the same with the N. So one of those permutations is Schottky, one of those is ohmic. And this is clearly the Schottky, and so the ohmic is the converse, which is here. Where this is N-type, and the Fermi level of the semiconductor is below the Fermi level of the metal. So therefore, the N-type semiconductor has to become more electron-rich with respect to the metal. And it's an N-type material, so to become more electron-rich, it simply herds all that available electrons to the surface. So this is not a depletion region. It's a puddle of electrons within the skin depth. This is basically how the Faraday cage effect works when the electrons reassemble on a perfect conductor to negate the lightning bolt, and so why you don't get electrified in your automobile, right? So the electrons on the skin depth of that perfect conductor the frame of your automobile are reassembling, and it's within a skin depth, which is related to the permittivity of the material. And it's only a few, just 50, 100 angstroms or so, less than 100 angstroms thick. So it's just this puddle of excess electrons. So it bends the bands very severely, very over a very short distance, and so therefore there's not an appreciable. There's a small little speed bump for electrons to go this way, and there's no speed bump for electrons to go the other way. So it ends up as being so instead of a. So when we say ohmic, just to be clear, this is a diode, right? But an ohmic is basically a resistor. It's a straight line. So it passes. It's going to drop very little voltage, but it's basically a short circuit. There is no. So the diode has the rectification where there's a nonlinearity, but a good ohmic contact is just a straight line. It's just a low resistor. So that's why we call it an ohmic, because it's behaving following Ohm's law.
And so that's formed with like an N-type semiconductor with a work function level lower than that of the.
Yeah, and then the holes similarly. You have the P-type material where the Fermi level of the P-type material is above the metal. So the P-type Fermi level of the semiconductor has to go lower to meet up with the metal. And so the only way to move the Fermi level of P-type material lower is to accumulate holes. So now the holes have very little impediment.
And so rather than a depletion region, is that an enhancement region?
Accumulation.
So is that different from enhancement? Because I've heard this from enhancement region before.
Yeah, I'd say accumulation, but yeah, enhancement works. That's why I'm careful, and to be quite honest, I know some of you text me about should I release an answer key for the exams. I want it to be in your own words. Long time ago, I used to give out answers to my problems, and then I found a period of time afterwards. I was seeing my own words, and that people had shared exams, and it was fairly clear to me that some students had not actually learned the material. They were just memorizing certain answers and parroting it back to me. And I would rather hear it in your own words. If you may use the wrong word, but I will, we'll get the gist. We'll understand the flavor. I want to hear in your own words that you learned it. That's important to me. I don't want you to parrot. I will probably use bigger words than you do or something like that. And so I want you to use it in a way that you're going to learn it, the way you're going to remember it. And so enhancements, accumulation, that all works for me. It gets the point across. Okay. What's the Las Vegas odds? Anybody know? Republicans, Democrats?
There is like this website that I know that like you can bet on anything. Like literally, like it'll be like smallest things, the biggest things. Like
Fiona Hill, are you turned off?
no.
Fiona Hill.